right, so in the interest of starting on time, I would first like to acknowledge that the land which many of us are on in Hamilton and at McMaster is the traditional territory of the Haudenosaunee and the Anishinaabe nations. The territory was subject to the Dish with One Spoon Wampum Belt Covenant, an agreement between the Iroquois Confederacy and the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. And I think it's important, especially today as American Thanksgiving, that we recognize our colonial history. And if you wish, you could post in the chat if you're on different traditional lands. I would now also like to welcome Dr. Mohammed Afzal, all the way from Seoul, Korea for us today. Hence a little bit of a switch in our normal time for these rounds. So he's an assistant professor and computer scientist who's done quite a bit of work on text mining and data analytics and informatics, and will be talking to us about text classification and summarization, which certainly I know for many of us in our research group is an area of interest. So I'm going to let you take it away, Dr. Afzal. Thank you and welcome.
Thank you, Dr. Lockyer, for the introduction, and thank you for the participants. They are here to hear this presentation. My topic is text classification and summarization, but during this topic, I'll be discussing some these are the topics of interest. During this presentation, we'll be talking about the word embeddings and the role of the word embeddings in the text classification and summarization. I'll be discussing some of my work in form of case studies. This will not be sequential, but sometimes contextual or appropriate where I want that this should be introduced. There I will be discussing about this. So there are two case studies that will be splitted around the slides. One is Biomed Summarizer, one is DASAN. So these two is our work, and that will be discussed as a case study or examples. So when we talk about text processing or text analysis, two things are very, very important. One is text classification and one is text summarization. And when we do summarization, sometimes we need classification before summarization. So these are different scenarios. In this case, we have classification as a standalone task. We have input as a text and we have output. Sometimes we do summarization without classification, but most of the times in this, when we have deep learnings and machine learning algorithms available, to have a good summarization, particularly abstractive summarization, or some cases the extractive summarization, we need classification. So it needs the garbage in, garbage out. We have to avoid that. Therefore, we have to take some simplification tasks before summarization. So that will be discussing during this presentation. So when either we do classification or summarization, doesn't matter. We need to work on the input. And when we want to work on the input, we have to look at the input source and the form of the input text. It could be structured or unstructured and from where it comes. So some pre-working we need to do. And this unstructured kind of text, we have to use natural language processing before classification and summarization. So I'm here to talk about this pipeline, NLP pipeline, that is the most important task in any of the name entity recognition, any NLP task, summarization, sentiment analysis, classification, or predictions, sentence prediction, etc. Whatsoever the task is, this we cannot avoid this pipeline. Of course, some steps in the pipeline could be avoided, but not as a whole. So when we usually, my discussion will be for the unstructured data, because structured data, we don't need this kind of processing. So that can be directly feed to the classification or summarization. But because the text processing by default refers to the unstructured text. So therefore, I'm discussing that pipeline in that context. So first, when we get the unstructured text from anywhere, no matter, we have some pre-process before going to even that pipeline. Like if suppose scientific literature on the COVID, I want to classify that text, then I have to bring the papers or the clinical trials research papers to my local database. Or if I'm working on the cloud or the cloud database. In the internal memory or the local memory is important, that should be arranged in a folders or some way that you can use in your pipelines or in algorithm. So that is a pre-process. We develop some custom programs, to download and to process the initial papers and remove the unwanted, for example, figures, tables, and unwanted text. And once we have that text, then we want to apply the normalization step. Normalization generally means the cleaning of the text. So when we have a text, we have to remove the, for example, HTML text, special text, or special tags. Similarly, we have to remove the brackets. And then after that, we reach to the tokenization. But before tokenization, I want to discuss one thing. Stemming and lemmatization sometimes required. For example, we have a words playing and plays and play. So the root word play should be there for most of the cases like name entity recognition. The ing or the s should be removed, and then we have one particular word like play. That other is the offshoot words that could be normalized to one. Stop word removal in most of the cases like is or am or the articles we remove, but sometimes we need that when, for example, the whole sentence as it is we want to use in some places, then we don't need to remove that one. Or for processing we have to remove and then we have to readjust them. After that, the most important step in the text analysis is tokenization, and that is the major topic of today's discussion. Tokenization, one is the simple tokenization that we do as a character level, that is like ASCII coding. We assign some numbers to the character, but most advanced level of encoding is the word encoding at a word level. So there is a problem with, for example, in the character level, there is no semantics in that. Same codes in different orders, and how to know sentiment of a word. For example, if you have two words, live and evil, these two are totally different words. But when we encode them as a character level, they have the same encoding, same codes, but in different order. So that's basically, there is no semantic. At the end of the day, evil and live will be considered as two similar or same words. That's the basic problem, because there is no semantics involved here. So therefore, we comes to the word level. Word level, we have some capability to capture semantics. For example, we have two sentences here. I live in Seoul City. I live in Seoul Town. Now, if we encode these kind of sentences, you can see that in these sentences, this part is totally similar. If we draw a cosine similarity or any other similarity technique, we will get, for example, 80% similar this sentence, and only the one part is different. So for that part will be considered as a different word. The other will be considered as similar. So there is some semantic capture already. So 80% this sentences will be considered as similar. So this is the basic baseline for the word embeddings or word encoding. But there are a lot of word encoding techniques, and there is a progress we made. Frequency-based encoding was very popular in the early 90s, and even later on, still we are using that in some cases. Frequency like term frequency, term occurrence, or TF-IDF, term frequencies, inverse document frequency. Those kind of techniques were used, and they were just depends on the frequency, the occurrence, the number of occurrence of a word in a document or a set of documents. Then we have one hot encoding, binary encoding, we have 1 and 0. For the occurrence, we have 1, and for the non-occurrence, we have 0. So these kind of techniques, frequency-based technique, the problem is there is, again, no semantics in that one, because just frequency. One hot encoding is a better technique because it's create vectors, but the curse of dimensionality problem is there. There was a lot of zeros for the unoccurrence of some word. You have to some fixed dimension, for example, 100 or 200, and then you have to put 0 for everything. So for example, if I have a color category and there are 3 colors, red, green, and blue, so I have to create 3 dimensions or three places for it. One will be for each color is 1 and the other 2 will be 0. If think about it, if it is 100 category, there is 100 categories in one attribute, then we have to create 100 places. All of them will be 99 will be 0, just 1 will be there. So this is a lot of 0, and the dimensionality, curse of dimensionality is a big problem. Then we come to the index encoding, integer encoding I didn't mention here. That was just replace the binary with some integer. Then we come to the real value encoding. Real value encoding is basically what we are today in the text mining or text processing world. A real value encoding was a breakthrough, great breakthrough. It was first in back 2013 when Google come up with the word-to-vec embedding. And but this kind of semantics, word semantics was not new, but the concept reappear in some other ways. Like in 1950, John first says, "You shall know a word by the company it keeps." Basically, this sentence refers to the word embedding. This sentence itself means that we have to consider the contextual, or the words in the surroundings, the company of the words that attach to that word. But it was not formalized in that way. In 2013, it was the first formalization, and it was a breakthrough, great breakthrough. Word-to-vec, and then global vectors, and then fast text by Facebook. And now we are in the world of BERT. In text classification summarization, BERT is the optimum. You can say is the latest and the very accurate and very enriched semantically and contextual. So most of the discussion will goes to the BERT today again. So in 2018, I think it's appeared in 2017, but as a preprint paper, it is published there. But then properly it was announced and released by Google in 2018. So it's a BERT bi-directional encoder representation from transformers. This BERT is different from the earlier models like word-to-vec or GLOW or fast text. I just mentioned 3 things, how it is different from them. One is feature vector length, number of factors, out of vocabulary. These 3 features are so unique and so important that BERT have, but the other previous model basically lacking. So let's discuss what is mean by feature vectors, the other model and the BERT model. What is the difference? Word-to-vec, for example, if you consider this example, it consider fixed length vectors. For example, you just consider 500 dimensions. So all the vectors will be created in that dimensions. It's a fixed. And order is not important. One word, one vector, and there is an index created. One word, one index. That one vector associated with that word. But in BERT, this is a dynamically informed word representation. It is not fixed. It's look at the surroundings and then creates the things. And order is important here. Order is important means context is captured by the order they have. They basically keep the order. In actually naturally, when we create sentences, order is really important. If we break that order, the semantics automatically lose. Number of vectors. Again, word-to-vec create only one vector for each word. But BERT, we have more than one words. Depends on the context, how many contexts that is used. So that's many vectors will be creating. For example, we have two sentences. One is I like apple fruit. One is I like Apple devices. If we create word embeddings with word2vec, there will be same vectors created for the both of the sentences, remember. But BERT will generate different embeddings for these two sentences. Now, one apple is a fruit, one apple is a device, it's a company name. It's totally different things, but spelling is same. So that's a big problem with the word2vec and other word embedding techniques. But BERT basically differentiate in these kind of different contexts. The context enrichment that brought by the BERT is a big breakthrough actually, and that is not available with the previous models. Out of vocabulary is another basically a problem with previous techniques. Like if I have this sentence, word embeddings introduced in 2013 was a breakthrough in NLP. This is a sentence. Now word2vec and BERT both basically all of the word embeddings create dictionaries. They have a trained dictionary, or the knowledge is stored in a dictionary form. But the problem is word2vec will not create any vector if that word is not available in the dictionary. Like embeddings, for example, is not available, so there will be not vector created for that. But BERT has a capability to break this embedding word into different subwords, which is called word pieces, and then according to that they create vectors for that. So this is how is different. Sometimes the subwords is not possible, then character level breaking also possible in BERT, and then they create vectors for that. So this is the architecture that is discussed. Attention in all you need. This was a preprint paper in 2017. They released this kind of architecture for the BERT, and BERT have a different mode of working. For example, here you can see BERT is taking two sentences. Here is one sentence. Here is used for the question answering task, like we have a query, like search engine, and then match with the paragraphs or the documents. And sometimes we use a single sentence tagging, like for example, one sentence we take and we associate some tag with that. So this kind of different models, modes of the BERT architecture we can utilize. And the working model or the working architecture of the BERT is input, like we have a text. If there are more than one sentences, one separate token is associated here, and clause is either is a single sentence or more than one sentence. Clause token is always be there. Then we have different encodings, and then after that we create this M into N matrix. This vertically you can see the rows are created for each sentences separated here. And these dimensions are created, like you choose how many dimensions you want to create. The BERT model is basically coming from the transformers. Transformers is a bi-directional, like bi-LSTM was a transformer. And it is based on that, but attention mechanism is added. So basically this journey is coming from like the recurrent models or enhance, and then we have one recurrent model as LSTM, which basically solve the problem of the short-term memory. And then like in RNN, we have a very short context capture, and if the sentence is long, become long, then the context was lost. To work on that problem, they introduce LSTM and then bi-LSTM. But bi-LSTM, then BERT added another layer, attention mechanism, so that they not only look at the long-term memory, but also the word level encoding, sentence level encoding, both are captured together. And then different variations introduced in the BERT, like for example, for patent BERT, Biomed, dog BERT, video, cyber, clinical BERT. These models are trained on different specific domains. For example, cyber, you can see scientific literature. It is built on the biomedical scientific literature. So this is what I mean, good model to use for when we apply some application like scientific literature classification or summarization. So in today's world, when we understand what this embedding the meaning of embedding and the classification or the text classification, we have to just the already available models. Then BERT tokenizer, for example, it is available in the transformers. We can easily import in Python, and then we can use for our own sentences to tokenize and to create embeddings for. For example, this is my sentence, and this sentence could be any. This is taken from the huggingface.co as a sample. Hello, my dog is cute. So the word embeddings will be created, or the tokenization with the help of tokenizer that is available in BERT tokenizer, which is coming from the transformer. So we don't need to do anything, just how to use them. And this the already pre-trained BERT-based uncased, and there are a BERT-based case model, and there are other models available. So what model you need, you just use them, and you create word embeddings for your own data. So that's how simple it is. The only thing we understand very well before using them. Otherwise, wrong model will be used for the for your own data. So once we have this NLP pre-processing, then the job is to use in some applications. For example, in text processing, annotation task is very, very important for this annotation is used for classification, for example, sometime for entity recognitions, sometime for sentence tagging. So annotation is very important, and these annotations or labeling are not available most of the times. And that is a big challenge. So we can use these pipelines for any of these tasks, either annotation, classification, or question answering or summarization. So we will be seeing at least 3 of these tasks, like annotation, classification, and text summarization. So first, let annotation task. For annotation task, when we have a text, but it is not annotated, that we have a text label is not available. If we have no label is available, that we cannot classify that text. So for that reason, if we have very little label data, so we have to increase them. For that reason, we need transfer active learning, the most popular technique these days. I want to discuss transfer learning, active learning, and then combine them one by one. So word embedding, when we talk about word embedding, the use of word embedding is in a different ways. Either we develop the embedding layer in our model, or we just borrow as a standalone model from the available pre-trained models. So this is a reusable of the available. This is a new learning. So either way you can use. So we talk about the standalone in this way, how we can use them. So when we talk about the transfer learning, the difference between the traditional machine learning and today's transfer learning is this one. If we have a data set 1, 2, 3, we have to create learning or feature learning for each data set separately, like this. But the transfer learning, the facility it provides is we learn one task, we create a feature set for that is learn on one task. For example, we learn the features on Wikipedia or WordNet dictionary. So those kind of bigger data learning is very challenging task for individual users or for small organizations. So this one-time learning is done and then it is available in the form of knowledge. And this knowledge can be reused for many other tasks. Sometimes exactly same task or sometimes similar tasks. So that is the reusability that transfer learning provides us. How we can do that? Before that, we also discuss one more thing and then we will combine. Active learning, a popular technique these days. Active learning is a technique that actually sometimes we have data, but it is unlabeled. We want to label it, then we use some oracle like human annotator. So we select some data and we present to the oracle, and then if the threshold of that data is less than some particular threshold, like for example 80%, less than 80%, we present to the oracle or human annotator, and then human annotates, and then we added those data, label data to the previous data, and then this cycle goes again and again, and we then come up with the increased number of label data. So that is the working model of the active learning. When we use active learning is the pure philosophy of the active learning is the query strategy. There are a lot of query strategies. One of them is stream-based, pool-based, and the membership-based. In pool-based, we have informative and representative, and then we have a lot of variations of the informative and representative. Let me discuss one strategy that is most popular is uncertainty pool-based strategy. In uncertainty, we select those instances from the unlabeled data that are least confident. The model is least confident on that. This means that in this strategy, we select those instances or those sentences of the text from the unlabeled text that if we provide to a model, it is most probable it will be incorrectly classified. So we bring those sentences first so that to present to the human annotator, and then if those inaccurate sentences become corrected, then in the later stages, the model accuracies will automatically become higher and higher and higher. So this is how it works. And there are some variation like least confident, margin sampling, entropy. Entropy basically have information, they use information gain. Here they are using selection, the posterior probability, and select the sample that is the instance that is least confident. I mean, the accuracy of that instance will be very, very less in the whole data that we provided as an unlabeled. So then we combine the active learning with the transfer learning. So the training model, we use embeddings from the pre-trained models so that this training model become enriched and the classification accuracy become increased. So one model we use in our own case study, that is recently we write a paper and it is submitted to IEEE Journal of Biomedical and Health Informatics. It is under review, but I'm just presenting the idea of one of the model. It's a little bit customized. Not exactly this is submitted there, but it's a little bit otherwise designed and changed. However, the overall idea is the same. So we have a clinical notes, initial label data, for example, 10 instances or 10 sentences or 20 whatsoever. These are label data. This is very, very less, and we want to increase them. And there is a lot of unlabeled data available here. We want to label this data. So first of all, this C data comes to BERT-based model. We use BERT-based model. This here, basically we use the transfer learning and not shown here. So we are using the pre-trained model of the BERT, and this is used in our model to create embedding and then classifying. And this label or classify, and we check the model accuracy. If it is very, very high, then we deploy directly. But of course, in the initial case, it will be very low. So we basically come here and we select other instances from the unlabeled data. Use the least competent query strategy. We select 10 more instances and then give to the BERT model classification model. And it predicted those examples. Now, if the threshold is higher, for example, 80% is our threshold, then we directly goes to the label data set and we add them. But if it is the threshold, the accuracy threshold, it is less than the threshold, for example, it is 70 or 60%, then we present to the human annotator. Human is very expensive, and because these experts are not available all the time, so we want to use for the least number of instances. Therefore, only those are presented that have accuracy less than threshold. Because here is a human annotate them, correct them, and suggest them, and those data goes to the label data set. Now, previously it was 10, now it become 20 in the maximum case, or some will be removed by the human, or we want to remove after the suggestion, then maybe some 18 or 17 whatsoever. Now our data set is increased. Now again the BERT model will check the accuracy. If it is the accuracy is higher, we will release the model. Otherwise, again, the other 10 sentences are selected. So this process goes on until we reach to the optimum accuracy that we want, for example, 90%. And then when we reach to that place, we release that model as a training model. Sometimes that training model is further increased in the later stages, but at least those sentences, the important thing is the label data set that we created become the training data set that used for the classification model. So text classification, again, there are two types, basic types of classification. One is binary, one is multi-class. Binary is two classes like sentiment analysis or the email spam checking, like email is spam or not. We have only two classes. So binary classification is used. Usually the accuracy of binary classification is very high. In multi-class case, the accuracies usually become lower than binary, but using the BERT model, now these multi-class accuracies also become very higher in the text classification examples. And we'll be discussing two examples like PICO and SOAP, that is multi-class. So first, let's discuss the binary case. And before that, there are some examples like how the classification algorithms are categorized. Like traditional machine learning, we have naive-based linear classifiers. Support vector machine was very, very popular for the text classification. Before the deep learning, we always use support vector machine, and we published them in, for example, 2017. We have one paper and we use support vector machine in that case. Then a simple ANN was also a good model, but its accuracy is not that high. And then we use deep learning neural networks. And CNN, LSTM, RNN, GRU, BiLSTM, and now BERT. BERT is the current and the recent model that people are using, and they are customizing BERT model for the classification, text classification. So for the binary case, we develop one system by Summariz. In that Summarizer system, there was one classification required, was quality classification model, where we need scientific sound studies to differentiate from the non-scientifically sound studies. So in this case, we have only two classes, positive and negative. So here is the model for this binary classification. We have biomedical literature documents. We have created data set positive and negative, and then we pre-process to create vectors from like a bag of words in this case. And in one model, we use word embeddings. Previously, we used the bag of words. And then we train model. In this case, we have deep learning, and then we boost them, and we use other boost on the deep learning, and then we apply that model for our case. And this was the binary classification. Previously, we used for the treatment, cancer treatment classification, the document related to treatment, cancer treatment. Now we use for the prognosis quality recognition of the brain aneurysm. I work with Henry Ford Hospital, USA, Michigan, USA, and we would develop one system for them and to differentiate quality documents from the non-quality in the prognosis for the brain aneurysm. That was used as a pre-model from before summarization. Here are some details, technical details, how many documents we have, like 2,686 documents, where these were the positives and these are the negative. For this, we use the clinical queries data. And for the negative classes, we use the PubMed query, the normal documents. So then we apply the model. And previously, we used the McMaster data and the clinical hedges data that is, I think Brian Haynes, maybe here, he was a co-author with me, and we work their data as a classification model, as a training data, and then we classify our data on that. And there are some of this model results that, for example, we compare with the traditional machine learning models, and then we get higher accuracy. For example, SPM was the higher top class before algorithm, that classification accuracy was very high before. But now I think the deep learning that we use, MLP, is at least 5 or 7% greater than that. And we check different variations and we get this optimum. And then when we apply the boosting, other boost on the deep learning, then we increase this accuracy to 97%. And the PICO classification is an example of multi-class. And we use this in the Biomed Summarizer. Again, we work with the Henry Ford Hospital for the summarization. So this case, we have PICO classes, but we also add a few more classes like aim and results. Usually, these kind of classes also required in some cases, so we use more classes than PICO. But generally, the PICO is the more well-known terms to use. Therefore, I'm using the PICO classification. And then for this, we use the BILSTM. You can see the input. This was imported, and we create embedding with the BILSTM. And then we have 5 classes. And these are the details, how many data we have. In this case, we have this much overall records, and this was the training, and this was the testing. And then there are other different details of the model. And finally, before summarization, we use the another case study, DASAN, which we summarize the text, clinical text in 4 classes: SO protocol, subjective, objective, assessment plan. In here, we have again multi-class study. In clinical text, you know the doctor when write the notes, they sometime writes the subjective part, sometime write the objective part, assessment part, and plan part. So we have to differentiate using the text classification technique. For here, we use the BERT model, and this is the architecture that we use. BERT we used, and also we use the semantic information network that we enrich the ontology, the text with ontologies. And then finally, we classify into the subjective, objective, assessment, and plan classes. And these are the technical details that we have used. And these are some results that we get from this model. Like when we use the CNN model, RNN model, BILSTM, and then combining with, for example, BERT, BERT, ROBERT, ALBERT, finally, our proposed was BERT with UMLS-based embedding. So one side was UMLS, one side was the BERT, and when we use this model, the accuracy was the maximum, 98% we achieve in this even multi-class study. That is so high, and using the previous SVM model, it was just 65. I'm not mentioning here, but SVM gives 65. And CNN was very low, RNN become greater, but optimum result we get with this model. BERT with UMLS based embedding. And we use 10 epochs here, and then you can see the different epochs, the accuracy was changing. So now the final thing that I want to discuss is the automatic text summarization. In summarization, we have two kind of variation. One is extractive summarization, one is abstractive summarization. In extractive summarization, we basically extract the original text. Although we can delete some part, we remove some part, but we do not change the original text usually. In abstractive, we change the original text and we create our own summary, but the overall meaning is not changed. Here, there will be a lot of grammatical errors because we remove some text, some phrases, but here the grammatical errors are not there because we create grammatically fixed text. I mean, we check grammar too when we generate the new summary. It is more difficult because we have to think about what sentence to represent the existing text. Here it is comparatively easier, but still there are challenges what to select and what to leave. So there are different techniques here, for example, frequency-based techniques, graph techniques, and matrix factorization techniques. But here also sentence compression kind of techniques are for abstractive. So I want to discuss one important thing. Either we use extractive summarization or abstractive summarization. We need to simplify the text first. How to simplify the text? A lot of techniques we can use, like syntactic simplification, lexical simplification, semantic compression, text normalization, text classification. We already checked the text normalization that we have to do before that. Text classification is optional, but sometimes we need, for example, in my model that I discussed before, we use two classification before going to the summarization, like binary classification and then multi-class classification. And then if you use the text classification, like for the quality model or the relevancy checking, it is improving the text to be input to the summarization. So your summary will be better as compared to if you do not classify before. Like if we did not check the quality of the text and we directly input to the summarization, of course, there will be less quality sentences included in the final summary. So then when we talk about the summarization, then there are a lot of variation we have to check, we are creating single document summary for the single document or multi-document. Because when we use the single document, the thinking, the final thing that we want to retrieve the sentences, how many clauses we have to include and exclude, that all depends on the choice of the input. And abstractive summary or extractive summary, that is another variation, what we have to choose in different content. And then the most important thing for what you're doing. So domain is important. It is a generic domain or query-based domain, informative or indicative. So everything, when we understand, and then accordingly we use the documents selection and the type of the summarization. In Biomed summarization, we use the extractive summarization. And this is the scenario I want to share with you what we did actually. In this summary, we create a query that was a detailed query, like how does family history affect rupture probability in intracranial aneurysm? Is it a significant factor? Now, this query, when we put, for example, to PubMed or clinical query, we will not be able to get any result in, for example, clinical query interface, because it's too huge query. Then we create abstraction on this query and take the important keywords like intracranial aneurysm family history. And then we bring, for example, for this, when we run in 2019, we get, for example, 239 studies overall. And then some studies were non-prognostic, and then we just remove them. 130 was included. When we run the quality classification model, only 74 were found as sound studies. We consider them positive studies, and other were negative and removed. So now this classification was so important that it removed the non-quality studies from the model. And then PICO classification used for the context capture, clinical context capturing, like population sentences, intervention sentences, and the outcome sentences. And then we use some other classes like aim and result as well for our purpose. Once we classify, and these are the statistics from these 74 overall sentences, and then we because in these documents different number of sentences will too many, and these are the included sentences as classified. And then we determine the semantic similarity. The semantic similarity determine between the query, detailed query, and the text that coming from here. But here we create embeddings, and then based on those embeddings, the similarity is created. Once we get the
Okay, looks like we have lost Dr. Afzal. Oh.
Yes.
Yes, you're back.
Okay, let me share again. It's okay now?
I don't see your screen.
Yes.
Nope. Yeah, I see you.
It is disconnecting. I don't know. Let me share again.
There we go.
It's okay?
Yes.
Okay. So we were here to discuss this Biomed summarizer system and how we create the summary. So once we determine the semantic similarity, and then we rank the sentences in different categories. So if it is a multiple document summary, sometimes we just created outcome summary. So in outcome, for example, we get 20 sentences. We don't need to present all the 20 sentences. Which one of those 20 sentences we have to present? And based on this score, we present not only similarity score, we also added a few more things like here you can see is similarity score is the relevance score that we determine, but we have the study type rank as well, and also the venue credibility score, and also the freshness score. And for example, venue credibility or study type, we conduct a survey from the doctors According to the domain, sometimes credibility change. When you credibility, for some cases, one journal has is more valuable as compared to another journal. So we basically arrange score according to the physician preferences, and we conduct a survey along from 10, at least 10 physicians. When we added all those scores, an aggregate score basically come here. You see here. Here is the aggregate score finally, and based on that we select some sentences and present. So this was the Biomed summarization, and just as a look in here is, for example, one document, and these are the different, sometime combination of sentences, sometimes one sentence, depends on the situation we have. And just because we have less time, I want to finish, but discussing some challenges and the future applications. Still, there are some challenges, and the researcher are working on that. Of course, many challenges have been removed. Like choosing the right combination from the available model is a big challenge. Everything is available, what to choose in what scenario. That is a big challenge again. It's not easy just to use blindly everything in every scenario. No, that's not workable. So right selection is a challenge. Unstructured text pre-processing overheads. You know, the 80% efforts always goes to the data processing actually, not the classification techniques or the other tasks. It's a pre-processing is basically a hurdle. How you do, how better you do that, how better we clean the text, that is one. Lacking label data availability. Although for each of these challenges, solutions are available, we have to work on that. Like human in the loop, active learning techniques or transfer active learning techniques helping in the label data availability. We have to increase those data. Black box nature, interpretability, as one speaker discussed here in this series as well. That is also people are working on explainability, they are increasing. But still, these are challenges people are working on. So let me share one the future scenarios with you. Like search engines are transforming. For example, Google has announced that they will be bringing BERT in even in the Google search engine. And then the people, when they ask from Google something, they will feel like a human feel like will be there. Like, for example, now if I search something, Google does not distinguish between the things, the semantically or contextual. But in future, we can expect that it will be coming. If they really use the BERT in internally in the server level or different level. Scientific literature classification. Always, when a new thing comes, always the data is unstructured. So quickly we have to transform to the structure so that it reach to the researcher and clinicians and physician, for example, in medical domain. So they create, for example, systematic reviews quickly and other recommendation system, decision support system they use in their system quickly. So that the benefits reach to the user or the patients as much as we can. So in that case, for example, when COVID-19 pandemic occurs, so a lot of literature was coming, research was coming. To interpret quickly and to present to the user, it takes time. But this model, I think these BERT-based models will bring them very quickly. Like McMaster is doing great job to classify the COVID documents quality-wise. And then I'm sure there is